So today, the two that we have is from Kenny and from Lasse. The one from Kenny is entitled T1234, a distortion-matched structural scan solution to misregistration of high-resolution fMRI data.
Okay, good morning, everyone.
We do have the notes here too, if you want.
Oh, really? Okay.
I can minimize this one.
Mm-hmm.
So you always see.
Okay.
Yeah.
All right. I have no financial interest to declare in regarding to this presentation. Many people in this room care about analyzing high-resolution fMRI signals, like this map here, across cortical layer profiles. We usually do so by means of taking reference image with gray matter surface, then to estimate layers, and ultimately extract signals across cortical layers. Unfortunately, this operation is not easy. The segmentation in this example look okay, but not perfect. You can see down here. The segmentation in this example looks okay. Yeah. The profile is surprisingly flat and blurry without a clear peak. This is frustrating, given there's a clear narrow peak visible in the activation map. Why is not there in the profile? This is because top-up and alignment is never work perfectly. What we want instead are surface like this that consider the geometric distortions and reveals a clear peak that we see in the activation map. In this abstract, I want to show how to get it right by means of an efficient acquisition tools that use our proposed protocol with matched distortions. In fact, this registration constraint has been identified as the single most limiting challenge in mesoscopic fMRI at the survey of the brain function study group back in 2018. The layer fMRI literature from the last decade is full of innovative approaches to address such registration issues by means of distortion-matched EPI. However, none of this approach has ever caught on just yet. Presumably, due to the fact that EPI is noisier, requiring extremely long acquisition times with whole brain coverage and averages. But also, EPI has issue of another dimension, which is EPI phase artifacts. The goal of this abstract is to take this 3D EPI approach, this one here, to mitigate both issues. Namely, we want a fast, distortion-matched, whole brain structural reference scan without EPI artifacts. Specifically, EPI is suffering from two forms of phase inconsistency. The geometric distortions that we want to be in full control of. But even without the distortions, you can still tell that this is an EPI image and not a flash. This is because of this kind of phase inconsistency that we call fuzzy ripples, which are unrelated to spatial signal misplacement. We aim to take control of both artifacts with the proposed protocol that we call T1234, a T1 weighted scan with 2 inversion times, a 3D EPI, and 4 spatial encoding directions, alternating both the phase and the read polarity. Combining all 4 of these complex value images give us a whole brain image without fuzzy ripples and adjustable distortions. Here, we have the complete sequence diagram. We use 14 segments to fill the K-space. Within each segment, we have an inversion recovery cycle to get 62 KZ partitions of 2 inversion times. Whereas each shard alternates between reverse and read phase polarity combination, respectively. We developed a blocked forward model that captures the T1 relaxation across the inversion recovery, and also along the relaxation. The 3D K-space is filled with each shard according to standard skipped KP approach. Across the shard parallel in KC, and across the TRs in the diagonal. With this model, we can optimize the gray and white matter contrast across protocol parameters. Specifically, we predict a combination of flip angles that give us the best compromise of signal strengths, point spread functions, noise propagation, B1 inhomogeneity, to ultimately make the data pushable through free server. Here, the red dot on the top is representing the maximum on this 3D surface. This parameter search is exemplified here. How we can get good SNR at no contrast, or no SNR, this one here, no SNR with mediocre contrast. With right flip angles, we are hitting the sweet spot. This blocked model can then also be inverted by means of a lookup table to convert measured signal ratios into a quantitative T1 values. This has comparable T1 histograms as we would expect it from amplitude range. With this protocol, the data give robust results of automatic tissue type segmentation across the major tools. Foremost important for layer fMRI. It works out of the box in free server with the quality level that we are used to get from amplitude range. We are also quite happy how stable it is across the participants. As seen across 12 people here, with run-to-run stability TSNR of 50. Since the 3D EPI acquisition is as fast as getting a whole brain volume in 20 seconds, this allows to do all kinds of fun readout gymnastics. Namely, we are approaching the time scales of typical fMRI block durations. So we could do a functional activation right during the structural acquisition, just alternating a checkerboard block across different averages. You can grab the second inversion time as T2 star weighted bold, while grabbing the T2 star free T1 weighted images for activation-dependent structural analysis. In this analysis here, the free server mostly detect a gray matter dilation at the white matter border. You can see here, are small but consistent. Different to non-visual area, like at the frontal cortex here, where you can get a feeling for the run-to-run surface location in inactivated areas. In conclusion, we developed a T1234 acquisition protocol that can give us gray matter borders and layer in EPI space with better spatial accuracy than amplitude range. Flipping back and forth between EPI and the structural scan, amplitude range is not as bad and captures the main layer profile. However, In this example, we are lucky that in a small section of the FOV, we have indication of intracortical patterns, like these two bumps in the deeper layers. With amplitude range, these faint signals are washed out into a prolonged tail. Only with the high spatial accuracy of T1, 2, 3, 4 surfaces, indication of these deeper blobs are visible in the profiles. I thank you for your attention.
Okay. Great. You are 10 minutes straight.
Are we ready?
Yeah.
Close. Not quite. Thank you.
You need 9 minutes.
Yeah, I have to cut something. Yeah, we have to cut something. Yeah. Mm-hmm. Okay, thank you.
I have a
Yes.
few really brief comments, but nothing like very big. On the slide where you say it's stable, I don't know, I think it's the 5th or 6th slide.
You mean this one?
Yeah, I would take out 7TA, 7TB. I would just say the models, because obviously they don't
Yeah.
know what those mean.
Yeah, probably they don't know what they mean.
So I would
Sure.
just say like across multiple teras and 7T plus.
Okay.
And
So-
then
Oh, sorry.
I think somebody's trying to.
Yeah, I think
I think
Peter,
Peter.
right?
I think Peter.
Peter, you had a comment?
No, I was just letting Tyler finish.
Yeah, my only other point was in the very first slide, you said something in your words that was not clear on the slide at the moment. You said there's a very clear peak that we're not seeing, but we haven't seen the blue line yet. So I would just reorder that somehow so that it's clear that like there is a very clear peak and then say it. Otherwise, people might be darting around to try to figure out what you're referring to.
Okay. We mean the slides, the
Yeah,
blue,
just
blue
put the
peak.
blue on
Okay.
earlier.
Okay.
And maybe have a legend that just says that the blue is after correction and the red is before or something.
Okay. Okay.
And that's all.
So I had a couple of just small comments and questions. So from the initial part, people initially think, well, okay, so you can use this. I mean, so one thing that's, I mean, it's not maybe not worth mentioning, but even as far back as the 90s, I mean, MGH knew that, you know, they would collect they had a T1 weighted scan that had the same readout window length as for their structurals. And so that's what they use all the time. They just never published it. I mean, it was for structurals. It was just basically to be distortion matched, but I don't know if they ever published it. But anyway, so just saying this is the first time ever in this context it is, but you know, people have been doing something like this for 30 years. At least MGH was. I think they were kind of unique with that. But in this context, so one thing that wasn't clear is that you can reverse the polarity of the gradients. But if you wanted to use this as a separate scan and then collect your EPI and then register the two, it wasn't clear what you would do. Would you just use half the data? You said you had adjustable distortion, and I'm not sure, that wasn't clear what that meant.
Okay.
Yeah, and I think it's actually kind of, you know, I mean, obviously there's many things that cause distortion, and you mentioned phase errors, but it's really, you know, the way I think of it, I mean, it's maybe to the audience, and they'll all be sophisticated, but I think it's nice to just simply say, well, you know, readout window length is you know, the big factor that causes distortion. And so, you know, with typical acquisitions, the readout window length is really short, equiplanar is really long. I mean, it's not perfectly correct, but it gets the point across. But one other thing too, one last thing, you kind of brush over this really quickly. You mentioned the lookup table, and then on the x-axis of the lookup table, you have assumptions. And that's a big thing because obviously getting quantitative TI is hard. the flip angle varies all over the place in space. And so those are big assumptions. People might jump all over that. But at least looks like the data are pretty good. I mean, so the big assumption is the flip angle over space, the flip angle versus T1. So the T1s, right, if you have different flip angles, it'll give you different T1 values, but because of the RF homogeneities, and if we could characterize those, then we don't have to make as many assumptions. But I don't know, you have limited time already, but
maybe I can talk a few, maybe with respect to the history, the first point, like we do mention that there are kind of many studies before that they tried it. I think MGH, who did it for layer fMRI, also after us, they never use it, right? And
right.
unclear.
Well,
and
yeah.
then I think the EPI just never really looks good enough that it can be pushed through FreeSurfer, and distortions come along with thin voxel dephasing, and then FreeSurfer is still kind of choking on that partly. So maybe we need to make it clearer how those studies kind of why they're not used, why they haven't caught on.
Yeah.
Then the readout links make sense. The assumption it's hard. Like we had this as a side note in the abstract where we described this more. I think because we are in the layer fMRI session, nobody cares about quantification. So we kind of made this very short. And the assumption is that kind of following the universal pulses, that each person, like they have a huge variance spatially of the flip angle. In the center, it's like factor 3, sometimes bigger than in the periphery. But that pattern is extremely consistent across people. So we can, what we did, we used a template of T1 for that coil in that scanner, which is extremely consistent across people, and then register that and do basically a universal pulse model in the analysis, not for PTX, but in the analysis, which kind of seems to get rid of almost all of that, which does not come across in this slide.
Yeah, that's a big point. Yeah, that's yeah, okay.
So if we add a B1 plus map as a template or something, then maybe that it gets clearer. And also the B1 map takes like 20 seconds. So
yeah, that's a good idea, actually. That's good. So once again, just really quickly though, how it was, you spent time talking about using this as the sequence for the functional scan, but what if people wanted to do a functional scan and then wanted to use this? How do you adjust? I mean, is that more that needs to be said? I mean, how would, like, this corrects distortions? I mean, this sort of like, does the double, but how would you match? I mean, would it correct the functional or would it match the functional scans?
It's an open question on how we want to sell it. So right now, the fastest protocol that takes 3 minutes corrects for the distortion. So we basically get both polarities, right, and then correct for it with top up on the left one, sorry, on that one. And we do the same thing for the functional. But however, since top up is never perfect, it still looks much better after correction with the distortion matched one. We also have a lot of data where we perfectly match the distortion, but then you adjust the readout, like the bandwidth of the readout, and then you not end up with a 3-minute protocol, but sometimes even a kind of 9-minute protocol. So it depends on kind of what you want to have, and maybe for us it depends on what we want to sell. Do we want to sell a kind of fast MP2 range that's distortion free, or do we want to sell something that has kind of adjustable distortions because retrospectively, because we know the distortions, or do we want to have something that's acquired with the identical distortion, but then takes longer? Kind of we try to check all of those boxes and provide solutions for all problems, but you're absolutely right. We don't have a clear kind of selling point or statement on how we propose people to use that. You have suggestions on what you might find the most usable?
Well, I would just put maybe a conclusion slide with exactly those 3 things that you said. You could do it this way, this way, this way, just have the options out there at the end. Just
I mean, because you have, I mean, it's the same brain that you're scanning in the functional stuff. Right. So, I mean, you could make suggestions for the future that, like, you could literally just give all the parameters of your API that you're using for functional, and it would recreate that. That's
Right.
not unlike the simulated MP2H that
Right.
people have done,
Right.
but with more information. You
Right.
actually have the information
Right.
that can make that model.
And we have those data to kind of show it in the conclusion slide.
Yeah.
Right. 3 next to that. Yeah.
And I thought the conclusion slide was very nice. It like really drove home what a big difference this can make. So I think you're in a good place for that. And
Great.
I mean, you don't want to like commit yourself to like this is what we're doing, but like you could easily say like this could be something that we could write a script for pretty easily.
Rüdi, you had your hands up.
Yeah, right. So first off, I think the presentation is very clean. I like that. But the points that have been addressed already, I think they are also important. And the distortion control is also one thing that did not become clear to me. So I assumed a little bit it was like taking from top up the field map and applying it in a way that you would like for matching the distortions. But then again, you also said that top up is not perfect, so it's kind of contradictory. It's difficult. But I think that's also critical. One other thing that might that you might want to change a little bit is that you have this final thing on the cortical thickness varying with function. With function activation. So I guess you should maybe call it like apparent cortical thickness or so, because probably what's changing is the contrast rather than the thickness itself. So I guess that people could also be very allergic to that, I assume.
And I agree with you. And it's a kind of from the references in the below, it is, yeah, there's a discussion. Maybe about that. It takes about 1.5 minutes to show that slide. I find it super cool because it's kind of something where you get function from the structured data. But is it too much out of place? Should I remove it? Should we remove it? Or
I agree with Rudy completely. I was going to make this point actually, and I think you might want to remove it because to fully discuss this aspect, like I would have expected to see how much the numerical stability varies if you just repeat the same T1, 2, 3, 4 acquisition like multiple times and push it the same way through FreeSurf, you know, because probably there is some variability due to small numerical changes in the input data. So like I would like to see this functional thickness change, whatever apparent thickness change, in the light of that baseline. Then it would be convincing, but this is like too much discussion, I guess, for this presentation.
On the bottom right, we kind of have the control, like to get a feel of the consistency of the thickness changes.
Okay.
Yeah. Like it varies too. It doesn't vary kind of in a consistent direction. We do have the data for the kind of repeatability because it's a very long experiment. We can, I mean, the kind of sneaky point why it's cool to include that is that I think it's just a T1 change that's just VASO. It's just VASO. It's always just a different T1 like value that you have during activity. But still, for like Saretskaya or other folks who looked at that, they say, oh, there's plasticity changing because they couldn't acquire it fast enough and they had to do these 6-minute flickering checkerboard. Now we come to the fMRI domain, and I think we have something to contribute to that discussion and say it's really only apparent signal changes. FreeSurf interprets this as it's not. It's just VASO. It's just a T1 change, which is too much information. Yes. Yes. Okay. And
yeah, that sounds pretty cool, but maybe too much. Yes, I would say.
Yes, too.
Yeah.
Just to make sure that I understand that, I mean, I know that the lines are the differences between the two analyses during activation or not, but the images don't look like they're changing.
They're not. Underlay is the mean.
Okay. Not for this talk, but someday it would be cool to show that story. And at that time, it would make sense to switch the images as well, just because like I think it'll become very apparent why FreeSurf is making that change.
I mean, yeah, you propose to change the underlay as you flip. Yeah,
Obviously, the images must look distinctly different.
like it's hard to see nakedly, like with a naked eye.
Well, that's even
Yeah.
good to know.
Right. Right. Okay.
So one thing to add is that, yeah, I mean, that's actually, so is that, it's just doing functional cortical depth imaging or functional, thickness imaging is kind of new, it's like a brand new thing in itself. I mean, and, people have been debating this for years. And so, whether things expand. So yeah, this is, I mean, that finding in itself is kind of amazing, if it's consistent.
Yeah, we see it across three people, but it's kind of a tangent to the story. Yeah,
It's a tangent, but it's, a lot of the other field would be jumping up and down over that.
It's a cool page.
It's a cool tangent. Okay. All right. We have a few comments, and we are halfway in.
Yeah, nothing. But actually, like now Peter said it. I was reading a paper yesterday about the like neurovascular coupling, and one of the alternative explanations for that was like plumbing system. Basically, arterioles vasodilation and so forth is a plumbing system. And there was this like non-Newtonian fluid perspective where you actually do the plumbing in the functionally active areas to like move the capillary, like move the stuff in the capillaries because the velocity there is really low. So I think like thinking of that, if you of course are convinced that this apparent thickness change or whatever is like true, this goes back very deep to the neurovascular coupling, right? Like this can be huge actually if we can convince ourselves that we detect it, and it is vasodilation and mechanical like change in the vascular network. Yeah, cool.
Yeah.
All right. Then if people have comments on specific slides or something, please get them to Kenny our way. We are halfway through, so I would like to switch to Lasse now. Could you see if you can share your screen?
Yep. Do you see it now? Huh? I can. The sound is very unclear now.
Allow me to put your presentation on the main screen. I think now I see you on the main screen. You can go ahead.
So Renzo, will you take time or?
I am. Yes. Yes.
Cool. Cool. Okay. One second. I want to get rid of this Zoom bar. I think it's gone now. All right. Yeah, so I'll start now then. So hello everyone. My name is Lasse Knusden, and the title of this presentation is NORDIC denoising on VASO data. So NORDIC denoising is a PVA-based denoising method that aims to suppress thermal noise from multidimensional MRI data. And it may be particularly useful for mesoscale fMRI, because in this regime is where the thermal noise is the dominant source of noise, as you can see down here. And we can use NORDIC to get rid of a lot of that noise. And this has profound impact on, for example, our activation maps, but also, for example, our t-values and our statistics in general. So this method has been extensively evaluated for gradient echo-bolt data across many studies now, but it has not been validated for VASO data yet. And VASO is this cerebral blood volume weighted fMRI method that is very popular in situations where we want high spatial specificity. So for example, in laminar fMRI. The thing though is that VASO is CNR limited compared to gradient echo-bolt, so it might be benefit even further from NORDIC denoising. So here our goal was to validate NORDIC on VASO data and specifically see how well does NORDIC suppress noise while retaining a signal. and also how should NORDIC be executed on VASO data. So the first study objective was to just evaluate the performance of NORDIC on VASO. And so ideally, we wanted to see the TSNR and t-values should go up. The percent signal change, on the other hand, should be left unaltered, because if NORDIC only removes thermal noise, then the response magnitude should not change on average. And then we wanted to see that the error across trials or the variance would decrease. So the second thing was to see how to execute NORDIC on VASO data, because VASO data has a different structure. So it is acquired, we acquire both these nulled or blood nulled images and not blood nulled images in an interleaved acquisition fashion. And so that begs the question whether we should do the denoising on this combined time series, or whether we should split it up into null and not null and then do the denoising separately. The second thing was to see if we should acquire an extra noise volume that can then be provided to NORDIC to give a direct estimate of the thermal noise level, or if we could skip that and just let NORDIC estimate the thermal noise level based on the data directly. And then finally, we checked whether we should do the denoising on the magnitude data only, or if we should also include the phase data to do the denoising on the full complex value data, as has been suggested or recommended for gradient echo bold data. So our approach was to test NORDIC across a range of field strengths and resolutions. And here we present a 3T VASO dataset from a single subject, but the generalizability across further datasets has been presented at this link here. So here we use the 3T segmented VASO dataset from this study, and the resolution was 0.9 millimeter isotropic, and we had 6 runs worth of data. And so the paradigm was bilateral finger tapping simultaneous with visual checkerboard stimulation. So therefore, our RI contained both sensory motor areas and also visual areas. And so it was a large RI with more than 7,000 voxels. And also we had many trials, which allowed us to do a lot of averaging, both across voxels and trials, which we could use to compute a nice ground truth estimate of the thermal noise-free case that we could use as a benchmark for NORDIC. So with a proper set of parameters, we found that NORDIC boosted the CNR and introduced minimal bias on the underlying signal. So when we evaluated just the noise suppression based on TSNR values, we found that the TSNR was increased across all of the different NORDIC versions compared to no-NORDIC, which was also the case when we looked at t-values as expected. And when we then did some quantification by averaging these TSNR and t-values across our RI, we found that the TSNR was boosted by a factor of around 2, whereas the t-values increased about 50%. And then from this quantification, we could also see that these 2 versions kind of stuck out from the rest of the NORDIC versions, which are highlighted here in green. So that would be the complex valued data version with a noise volume. And based on noise suppression only, it seems like these versions might be the preferred ones. But when we then looked into the amount of signal preservation across the different NORDIC versions, we got a different story. So here we evaluate the percent signal change averaged across all of the voxels in the RI with and without NORDIC. And then if NORDIC preserved the signal, we should see these that the percent signal change across each of the trials was left unaltered. And what we found here is that this version down here highlighted in green seemed to be the best one in terms of preserving the signal. We had these mostly flat lines across trials. And this version was the magnitude only with a noise volume, and where the denoising was performed separately on null and not null time series. On the other hand, these versions up here that showed the best noise suppression seem to be some of the versions that resulted in most signal loss. So there seems to be this trade-off between CNR improvement and introduction of bias, which I'll try to demonstrate over here. So NORDIC has this flexibility that we can boost this parameter called the scaling factor, which can remove more principal components and therefore lead to more aggressive denoising. And we see that when we keep increasing the aggressiveness or increasing the scaling factor, we get more and more robust activation, higher T values, and we start seeing activation even in these regions up here that were not visible in the no-NORDIC case. But what we also see is that as we increase the aggressiveness, we start introducing more and more bias, so the percent signal changes start going towards 0. And so we need to be aware about this bias. And so that suggests that we cannot just evaluate our denoising performance just based on the amount of noise suppression. We also need to take into account the signal preservation. And in this regard, we like this version the best. So we zoomed in on this version a little bit and made some more tests to evaluate its performance further. And here we show the mean of the difference time series, which represents what NORDIC is removing from the data. And we see that within the brain, there's no clear structure, except that it is scaled by the G-factor map, which is what we expect if NORDIC does not introduce smoothing into the data. Then we also see that the laminar profiles extracted from this RI down here in the visual cortex, they nicely converged between no-NORDIC and NORDIC, as we expect when we average across many trials. And at the same time, the error bars for the NORDIC profile is smaller. Then here we evaluated finally the percent signal change as a function of trial number. And here we see that the true signal variability across trials that is not related to thermal noise seems to be preserved even after denoising. So in conclusion, based on this data set, we recommend to perform the denoising for VASO data on separate time series with an appended noise volume and on magnitude-only data. And this is not to suggest that this is definitively the best version, but we do want to say that it appeared that by doing the denoising in this way, it seems that the spatiotemporal structure appeared well preserved, and that allowed us to boost the sensitivity of VASO in a safe manner. Thank you.
Thanks a lot. You are at 9 minutes roughly. I think you have 8 minutes for the talk, right?
Right.
For the video.
Right.
I like it a lot. It's a clear kind of coherent story. I have a few comments. Maybe the first one is maybe for the sequence. You reference where the data are coming from, but maybe I'll send you some few references on kind of more about that sequence so people kind of know exactly how it's not trivial to get good phase data and how this is all estimated, what's the readout and so on. For the aggressive slide that I love, because it kind of summarizes that NORDIC is neither good or bad. It's just a matter of that one. Maybe, like you say, it's preserving signal versus noise removal. Maybe you can also mention the spatial integrity, because at the bottom right, like it's not at the voxels where there should be activity. White matter is all over the place. And maybe you can even see the patches of the noise, like the kernels. So there it is putting signal at places where it shouldn't be. If it's not... maybe we should mention it. For the G-factor map, I remember we acquired the G-factor map, the one that's estimated from ISPEP. This is not the one you're showing at the bottom. This is the one that NORDIC estimates, right?
Right.
Maybe you can, that this is the kind of estimated G-factor based on this MPPCA, what that is like the estimated G-factor, not the kind of measured G-factor.
Okay.
Also, you have this awesome wrapper that's kind of on GitHub and available for everyone, which kind of exactly uses the sequence and kind of the nomenclature of how they are separated, like used in all the VASO users. Maybe you can include the link and say, hey, here's the wrapper, and this is the kind of fail-safe thing that we optimized. You can download it and use it.
Makes sense. So do you think we could just add that at the conclusion slide, or
that would make sense?
Would that be appropriate? Okay. Cool.
So I had a quick I mean, if you can go back to that slide that runs So, I mean, some people might interpret, so yes, the percent signal change goes down, and you generally, obviously, you don't want that, but it seems image as, oh, the contrast is still going up because you're detecting all this additional activation that you couldn't detect before. So I think it's, it's, people might argue that and I'm also curious if you kept
Peter, sorry, I don't know if it's my computer, but there was an interruption, so I didn't hear I didn't hear your point clear.
Well, my point is that people might interpret as being like.
Can I say it again? Sorry, Peter. What might people might interpret?
Is there a problem with my computer? I wonder. People might interpret this scale factor 5 map, the map on the bottom right, as they might think that that there's more there that you're detecting, and there, so it as opposed to, maybe in these areas you could maybe, and maybe it is. I mean, I actually don't know for sure. I mean, those are frontal eye fields. They are.
You don't have
So just a thought that might actually not be. I mean, it would be interesting also to see how, if you keep on percent change go down to 0, and then what does the contrast to noise map look like? So yeah.
Yeah, thanks, Peter. I think you're making a good point, but I didn't get all of it because there's some lag. I don't know if it's my end or, but
I heard the same, Lasse. Like there was a second gap every 5-6 seconds when Peter was talking.
Right.
Might be my computer doing something weird. I guess, yeah, so can you hear me now? Is it clear?
Yeah. No, not now.
Oops.
I think if we got a point though, that that we don't have a ground truth, right? So do we want white matter activity? Can we really say that this is all false activity? Do we want more activity, or is there anything like false positives? We know from Javier that there isn't.
Yeah, I mean, anyway.
Yeah, but here in this case, it's just so hard to know if it's false positives, right? Because we don't know if the white matter activation, is that something that we now see because we removed all this thermal noise, or is it smoothing that is being introduced, or from the gray matter, or what is that's hard to tell, I think.
I think Peter was maybe suggesting something like without the threshold, just showing the contrast, like maybe next to the figure or so. And then you would kind of see how it, like if it generates signal maybe, or if it's just generating signal above the threshold.
Right. And I think and I really do think that as a further experiment to increase the scaling factor and see what happens to the percent signal change versus the contrast to noise, and then see what the maps look like if you go out to like 10, or keep on iterating. So I'm kind of curious.
Right.
Eventually, I don't know. It would be interesting.
Yeah, I agree, and we have played around with this a little bit. I don't think we got much higher than 5, but we saw already here some interesting effects. For example, that I don't know exactly where the threshold was, but at some point we start removing the motion also. So if you make a movie of the time series, all of the motion is gone, which I found quite interesting.
Interesting.
Yeah.
That's expected though, because NORDIC works over like space and time, right? So it basically concatenates the voxels over space and time and does like a low rank reconstruction, which is like a projective version of it that is at the end like a summary. So you are basically simplifying the structure that you have in space-time. So that is to me well expected, like reducing motion and other time effects.
Yeah, it makes perfect sense, and I think it's a fun way to play around with the scaling factor, and see these effects.
What does the scaling factor do? I missed that part, I think, like exactly in the algorithm.
It's called in NORDIC, I think it's the factor error argument. So the default value is 1, and then you can just increase it. So if you put it at 1.1, it will increase the noise threshold by 10%.
So it is like determining the cutoff that
Yeah.
it
Yeah,
zeroes
yeah.
out the components after
Exactly.
a singular value decomposition. Okay.
Yeah.
So it's like higher values means that it is zeroing out more components before
Yeah.
it.
So
Okay,
it becomes more aggressive. Yeah.
I see. Okay.
Mike works if you would.
Yeah.
Tyler has a comment.
It's more just a question. It's similar to what Farouk was talking about.
Yeah.
Like my understanding of it, and Luca, if you have more information, that's awesome. But I think that the scaling factor is like the default of NORDIC is 1, and then it's a multiplicative factor of how many things you're cutting out. That's the way that I've always interpreted it. It might be interesting in the future to actually look at it as like also the rank of the reconstruction that you're doing then, because eventually if you pushed the scaling factor all the way to the point where the rank was 1, that would be the equivalent of only looking at the global signal, I guess, as like everything is just one time series combined. So that might be really useful information for people to just understand what is it doing to the data literally, like, because it's a quantitative reconstruction, obviously, or it's an incremental quantitative reconstruction. Does that make sense, Lasse?
Yeah, I think so. So you mean you could set a parameter that explicitly states the number of components that you want to
That are
contain or remove?
yeah. So like
Yeah,
obviously NORDIC is like in a data-driven way deciding how many things to cut out.
right.
Of course, you could also make the actual measurement using the PCA. How many components do we have left? And you can do
Yeah.
the reconstruction anytime, anywhere between 1, or technically 0, but 1, and the number of time points that you actually have in the analysis. I think that
Right.
that's your range that you have.
Yeah, that would be cool. I agree.
It might just give you an extra piece of information that like intuitively tells you what's happening when you do this.
Right. Yeah, and I also think it would be cool if we could see the components, like what do they look like? Do they look like the highest principal components, do they look like signal? Or I think that would also be very informative. And I don't know if that option already is there. I don't, is Luca here now?
Yeah, the option is there. There's a flag to save the components that you removed. So you can see, you can quantify the number of components and see the components that are removed. I don't remember exactly the flag, sorry, but it's in there, it's in the help. You're absolutely right about the threshold is the SVT, is basically determining how aggressive you are on your singular thresholding. So yeah, and I never thought about the rank, I think, but yeah, sounds interesting. I think about a little bit more. Another thing that we're thinking about as well, relative to like limited number of components, that we're trying to work on it right now, but I'm not sure. Well, obviously with ISMRM and stuff, one thing that we can try to do is like remove different number of components in K space depending on where you are in K space. So in the middle of K space, you know that you got low frequencies, so you can get away with like higher removal, and when you're at the edge of K space, higher spatial frequency. So maybe preserving more components, removing less, so less aggressive removal on the edge of K space and more aggressive removal in the middle of K space. So kind of like an adaptive removal in K space opposed to image space. Yeah, and my two very, very small comments. One is when you say best noise removal, just because you're suppressing more noise is not necessarily the best noise removal, which I don't know if that's what Renzo meant. So when you're saying like, looking at that TSNR, this goes higher. So best noise removal, just say the most aggressive or the highest removal components or whatever, because you know, you don't have any means to evaluate whether it's the best or not. And I forgot my second point, but I had, and the second point was, and I think Renzo briefly touched upon it, is the usefulness of the, in theory, in a purely theoretical framework. Obviously, in complex space, if you have an ideal complex space, you should do the best job, because in complex space, your noise should be Gaussian. As you move to image space, it becomes Rician, which might have some structure in it, depending on context and so forth. But it becomes highly dependent on the context of your scenario. If your phase images are very noisy, then you're doing more damage than you're doing good, right? So, and I don't think that you've commented on that, but maybe it's too deep in the 9 minutes talk, but just the phase images, the quality of the phase images will impact whether adding, you know, performing noise on magnitude only or on phase and magnitude will do a better or worse job. I don't know if that was clear, but
yeah, makes perfect sense. And I did not mention anything about that now, mainly in the interest of time.
yeah,
But maybe, yeah, but
maybe
maybe I can squeeze it in somewhere.
I think you're fine, because at the end you do say in this context, and you say it's not necessarily generalizable, so you kind of like, you know, it's like a way out there. But I would be interested, because we talked about it before as well, obviously offline and stuff, but it'd be interesting to know the quality of your phase images when you're doing VASO at 3T as well, which I imagine will be not very good.
I think the weird thing in VASO is that you have this flip, right? That sometimes the magnetization is in the opposite phase encoding direction, which really screws up the phase with respect to the assumptions in NORDIC. Like sometimes you have these shifts of 180 degree, which I guess might be one reason why we are not happy with using the phase. Yeah. So if you mention the phase, Lasse, maybe mention that the phase is weird in VASO due to the inversion recovery. Maybe a formal point, maybe you read the guidelines and I didn't, but you don't have a title slide or this conflict of interest thing, right?
Yeah.
They have a general title slide then, do they?
Yeah, so for the title slide, they say they recommend that you just have some like summary figure, and then they will add all the titles and everything.
Okay.
Yeah, so you shouldn't add that, I think. You shouldn't do that yourself, I think. Then it will be there twice in the final version. And the disclosure slide is optional for digital posters. Yeah.
Cool. I made a screenshot of Peter's written comments. You saw them too, Lasse, right?
No, I haven't seen them.
More ideas on how to make more out of the scaling factor graph, more measures to
Cool.
They just kind of summarize what I said, more or less.
Okay, perfect. Thank you, Peter.
Sure.
Are there any further comments?
Lasse, where are you? Are you in Asia?
Yeah, I'm in China right now.
Oh, thanks for staying up late then. Okay, wow.
No problem.
Midnight.
My pleasure.
All right, then thanks everyone. Next time I will put it in the reminder. We will probably meet for longer than 1 hour, and we will continue with ISMRM presentations. I think Tyler will show 2 presentations. I will show 1, and maybe Burak will also show 1. All right, then see you in 2 weeks. Bye-bye.
Bye.
Bye.